Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 5.1.3, which is the zero product property. Our path begins on problem 5-26, which states, what do you need to sketch a parabola? In other words, how many points do we need if we were going to sketch the graph? In part A, it says, can you make a sketch of a parabola if you only know where its y-intercept is? For example, if you know the y-intercept is at 0, negative 15. Can we sketch the graph? Let's see. If we have a point here, 0, negative 15. Well, at this point, I don't think we have enough information for anything. It could be just a point right there. It could be a line, or it could be an exponential. We don't really have enough information here, so definitely not. There's just not enough information with 1 point. So not enough info with only 1 point. And I would even say we do not even know what type of function we could be graphing with only 1 point. That takes care of A. I would assume that would have been relatively obvious. In B, it says, what about the two x-intercepts of the parabola? If we only knew the x-intercepts, could you sketch the parabola? For example, if they were negative 3, 0, and 5, 0. So let's find out. We have a parabola at negative 3, 0, and at 5, 0. And I'm just kind of roughly, and they did say sketch, so we have more information now, and because it's a parabola, we know that it's going to be going like this, right? We know that it could be going like this, right? The issue with only having the x-intercepts is we don't exactly know where the vertex is. And so while I said that the parabola definitely moves like that, that's actually a bit of a misnomer, because the parabola, as we saw in the last section, could also have been going downward. And so we don't really know what type of parabola we're dealing with. So I believe just the x-intercepts alone are still not going to be enough. So let's write that down. Just the x-intercepts alone will also be insufficient, because we do not know let's say the facing of the parabola, if it is upwards or downwards. We also don't know the width of the parabola. The width of the parabola could be, so right now the parabola is, say, this much wide, but there's also another version of this parabola that could be really, really, really thin, and it could extend way down like this and be thinner on the way up. Right? We just don't know where it is. So based on just those 3 points, based on those 2 points alone, I don't think we have enough for an actual parabola, although we can conclude that it would be U-shaped. So we're getting closer. And then the last one says, can you make a sketch of a parabola with only two x-intercepts and a y-intercept? And I think this one might actually be it. So we're going to combine both ideas. So the x-intercept's given in part B and the y-intercept given in part A. So let's take a look at what that looks like. Let's see here. So it looks like we have the points negative 3, 0, 5, 0, and 0, negative 15. And so from here, negative 1, 2, 3, 0. 1, 2, 3, 4, 5, 0. And then 0, negative 15 is going to be like right down here. And, you know, honestly, like I think that might be enough. I mean, we might be able to say, generally speaking, it's going to pass through, whoops, and my scaling's a little bit off, but that's okay. We know that the parabola is going to be symmetrical like that. So I think, yeah, I think we have a general knowledge of what the parabola is going to look like. We know that it's going to be upward facing. The reason why is because there's no reason why a parabola would do this, right? Go downward facing and all of a sudden double back and hit the y-intercept like that. And so I feel like this one, generally speaking, could be assumed upward facing. So yes, with this, we may have enough info for a general sketch of the parabola. So what this problem is trying to get us to understand is that we would need at least 3 points in order to graph a parabola effectively. I'll be right back with the next example. And in 5-27, it says in the previous problem, you learned that if you have the intercepts of the parabola, then you can sketch the graph without making a table. But how can you determine the intercepts of the parabola from its equation? So let's talk about what intercepts actually are. It says what is true about all of the y values for all the x-intercepts, and then the x value for all the y-intercepts. So we know that when we have a y-intercept, we let x equals 0. And that is why, and so if you need an example of this, like in y equals mx plus b, right? If I did y equals 3x minus 7, we know that the y-intercept is 0, negative 7. And that's because if I let x become 0, negative 7 is the only thing that survives. So we can say we let x become 0. And so I'll go and give a few examples. Like we would have 0, comma 3, 0, comma 5, 0, comma negative 5. And it's always 0, comma number, right? And that's because the x-coordinate is always 0, right? When we have a y-intercept, the x-coordinate is always 0 for a y-intercept. And so again, if I had to draw this graphically, if I had to draw like some kind of like intersection right there, that's 0, comma some number. For an x-intercept, I'll go and write it out over here. An x-intercept, we let y become 0. So again, those coordinates are manifested as some number, comma 0. So like 7, comma 0, negative 12, comma 0, some number, comma 0 always. And in this case, in the x-intercept, we say that the y-coordinate is always 0 for an x-intercept. And again, if you needed that drawn out, if you look at a curve that looks kind of like this, right? All of these points are resting on the x-axis. So we all know this is going to be some number, comma 0, because we're literally not elevated at all. So that is the basic premise behind intercepts of a graph. Let's go and apply the y-intercept into B here, where they say they want us to find the y-intercept of 2x squared plus 5x minus 12. So again, to find the y-intercept, I let x become 0. So I don't have y equals 2x squared anymore. I've got 2 times 0 squared. I don't have plus 5x anymore. I have plus 5 times 0 and then minus 12. These guys are going to go away and I have y equals negative 12. Well, what does that mean? It means that our y-intercept is 0, comma negative 12, which means this thing passes the y-axis, the vertical axis, at 0, negative 12. So there's finding the y-intercept of this equation. And then it says, what equation would you need to solve to determine the x-intercepts? Well, remember, x-intercepts means we let y become 0 this time. So that's going to be 0 equals 2x squared plus 5x minus 12. And so right now, this is what we have. And at this time in part D, they're asking us, do we have the tools or do we have a solution or a mechanism to find the solution to this? And honestly, I don't think we have one right now. But what they're telling us is that these are called the zeros of the function. When you have something called the zeros, it means you have an x-intercept. So let's go ahead and write that down. Zeros means x-intercept. So I'm going to go ahead and use those terms interchangeably. So hopefully you don't get too confused when you hear me interchange between them. But right now we don't have a mechanism to solve this. We currently do not have a means to solve 0 equals 2x squared plus 5x minus 12. We've never solved a quadratic equation before. And so I think that's going to be the point of the next problem. Give me a second. And here we are at 5-28. We're on something known as the zero product property, which actually is the name of this lesson. It says the equation you wrote in part C of problem 5-27 is called a quadratic equation. To solve it, you need to examine what you need to know about 0. And it says study the special properties of 0 below. So we're looking at Nathan, Nancy, and Gaston. And they're playing a game where Nathan and Nancy think of a number, and then they give Gaston a clue about their numbers. And it says, using the clue, Gaston must tell them everything he knows about their numbers. So in part A, it says, Nathan and Nancy's first clue for Gaston is when you multiply the numbers together, the result is 0. Well, what result can Gaston make from that? Well, what we're hearing about in part A is that if we have, like, say, some number, I'll just call it like x sub 1, times some other number, so x sub 2. So let's say Nathan's number is x sub 1 and Nancy's number is x sub 2. Somehow we get 0. Well, hopefully you can kind of understand that Gaston can very easily come to the conclusion that either x sub 1 is equal to 0, or x sub 2 is equal to 0, or both. And the reason why is because when you multiply two things together and get 0, you know that one of the things has got to be 0. So let's go and write that down. One of the numbers, and let's go and get that here. Yep, one of the numbers must be 0 because the product of the two numbers was 0. And 0 is really the only one that can do that, right? Multiplying something by 1/2 doesn't turn something into 0. You know, multiplying something by a negative value doesn't change it into 0. Only multiplying something by 0 makes it 0. And it says, disappointed that Gaston comes close to figuring out their numbers, Nathan and Nancy invite Nadia over to make things harder. And then they think of their secret numbers. And this time they said that when their three numbers are multiplied together, the answer is still 0. What conclusion can Gaston make? Well, again, it doesn't matter. We'll throw Nancy into the mix. We'll throw all kinds of people into the mix. But if you multiply three things together to get 0, that means that either the first thing is 0, the second thing is 0, or the third thing is 0, right? These are or, and it could be all three of them were 0, right? You know, there's no way to know, but we do know this, and that is that at least one of these three numbers must be 0 again. Because again, it's that whole idea. The only way we're going to get 0 is if we multiply 0 into the mix to get 0 out. And it says, does it matter how many numbers are multiplied in part C? If the product is 0, what do we know about at least one of the numbers? And they're trying to get you to understand something called the zero product property. And that's what this is. If I write down the zero product property, the zero product property says if the product of two or more numbers is 0, then you know that one of the numbers must be 0. Now, instead of numbers, we're going to use terms in this next problem, but I think you'll kind of get the general idea. Let me go and copy and paste the next problem in, and we'll see how the zero product property is actually used. I'm hoping that you'll guess that it's going to be used here with this part C. So I'll be back in a flash. And here we are with 5-29. It says, now you will use the zero product property to write the quadratic equation and solve. So from here, what we're going to do is we're going to rewrite the equation as a product equal to 0. So right now, going back to this idea, we have an area written as a sum. We've got 2x squared plus 5x minus 12 is equal to 0. And we're going to write that as an area as a product. And so I'm going to go and bust out our good old area model on this thing. So negative 24x squared with a 5x down here. Two numbers that do these are going to be 8x and negative 3x. So in my area model we go, where we have 2x squared and negative 12. This becomes an 3x negative and an 8x down here. That tells me that a 2x and an x goes here with a minus 3 and a plus 4. And so now what we have is 2x minus 3 times x plus 4 is now equal to 0. So why is this useful? Well, go back to the zero product property. If two or more things are being multiplied to equal 0, that means that at least one of those things is going to be equal to 0. So now what I'm going to do is I'm going to replace this guy with an x sub 1 and replace this guy with an x sub 2 and use the zero product property. And say that means that either x sub 1 has to equal 0 or x sub 2 has to equal 0. So remember that, right? You don't have to show this when you're doing it, but this is kind of what I'm thinking. And so now moving over to this side of the board here, I can then say, all right, if this set equal to 0, then either 2x minus 3 will be equal to 0 or x plus 4 will be equal to 0. And now we've just got a couple of integrated 1 problems that we're dealing with where we're going to add 3 to either side. Whoops. And I get 2x equals 3 divided by 2, x equals 3 halves. And then I subtract 4 from either side, and I get x equals negative 4. So what did we just find in the context of this problem here? Well, I'm going to go all the way to the right side here. Because I set the problem equal to 0, I let y equal 0 and got 2 values of x. What I have found is that this graph has 2 x-intercepts, one at 3 halves, 0, and the other one at negative 4, 0, right? That was the whole point of the whole problem, was to find the x-intercepts. We know that the y-intercept, if we look at this thing, if we let this thing become, all the x's become 0, that means that I'm going to do y equals 2 times 0 squared plus 5 times 0 minus 12. Looks like I'm going to get 0, negative 12. And I do believe that this is probably enough information to at least sketch out this parabola here, where what I'm going to have is, let's see, 1, 2, 3, 4, 5 here, 1, 2, 3, 4, and then I'll just throw down 0, negative 12 down here. It's not a big deal. 0, negative 12, negative 4, 0, and then positive 3 halves is about 1.5. And here we go. We're going to just go and kind of, and right now we're not really going to be too worried about where the vertex is. We'll talk about that in a later chapter. But that is what the zero product property allows us to do. It allows us to find the x-intercepts of a parabola. This is why we've been factoring so much these last couple of weeks, because factoring is now slowly but surely becoming a smaller step in a larger problem. I'm going to be back with the next example, but welcome to what we use factoring for. I'll be right back. And in this next problem here, it says another useful point on the parabola is the vertex. How can you use the x-intercepts of a parabola to locate the vertex? Let's go ahead and do that real quick. So in part A, we're going to use the zero product property again. So instead of y equals x squared plus 4x minus 5, I'm going to get 0 equals x squared plus 4x minus 5. And again, why did I set it equal to 0? I set it equal to 0 because in every single x-intercept we have, the y-coordinate is always equal to 0. So in fact, I'll probably just go ahead and write that out right now. It's going to be something, 0, and presumably something else, 0. And we'll go and do the y-intercept also. That's not that bad. It's 0 plus 0 minus 5, so 0, negative 5. We'll go and find the vertex in a little bit. So the vertex. Okay, so now from here, I'm actually going to go and factor this thing the fast way because it's pretty straightforward. I know the x squared breaks apart into x and x. The 5 will become a 5 and a 1. And I know I can get a a positive 4 if the 5 is positive and the 1 is negative. So again, what does this allow me to do? It allows me to say that because two things being multiplied together equals 0, that means that either the first thing will equal 0 or the second thing will equal 0. So if I subtract 5 from either side, I get x equals negative 5. If I add 1 to both sides, I get x equals 1. And that tells me that the x-intercepts are at negative 5, 0 and 1, 0. So let's go ahead and graph those points real quick here. And actually, you know what? I'm going to go and grab an actual coordinate plane. That way it's a little better looking. Give me a second. I'll be right back. And I'm back, and I've got this huge coordinate plane right here. It might be a little larger than I was thinking, but that's all right. We can go and punch these points in. I'm going to use a darker blue. That way it contrasts on the white background more. But here's negative 5, 0, and 1, 0. Oops, 1, 0. And then my y-intercept is 0, negative 5, which is down here. So if I was a betting person, I would guess my vertex is on the left side of the axis, of the y-axis, because I'm more heavy on the 5 than I am on the 1. So as we saw with the the water balloon toss, the vertex was always in the dead center of the parabola. And so what I'm going to do is I'm going to go ahead and average the x coordinates of my x-intercepts here. So I'm going to say negative 5 plus 1, and I'm going to divide them by 2. So that's the average distance between them. And so that's going to be negative 4 over 2, and that's going to be negative 2. So what did I just find? I just found the average distance between, or the halfway distance between the x-intercepts. And we saw that happen in the water balloon problem, where the vertex was always equidistant away from the point of launch to the point of landing. So I know now that the vertex is going to be negative 2 comma something. Well, how do I find that comma something? Well, what I'm going to do is I'm going to plug that negative 2 into the original equation. So I'm going to say y is equal to negative 2 squared, not x squared, plus 4, not x, but negative 2 minus 5. That becomes a 4 minus 8 minus 5. So 4 minus 8 is negative 4, minus 5 more is negative 9. So I know my vertex is at negative 2, negative 9. So I'll go ahead and punch that guy over to here. So negative 2, negative 9. And I will go ahead and connect those points together. And there is my more accurate quadratic. So today we learned zero product property, a very, very important aspect of quadratics. Please remember zero product property. And please remember that whenever you're solving a quadratic or polynomial equation, you'll always set that quadratic or polynomial equal to 0 and then use the zero product property on some level in order to solve for the values of x. I hope you found this useful. As always, please leave comments or questions in the comments area, and I will see you in the next episode.